So we are moving on with the next presentation. How is it called? Gwenel. Okay. I thought that Greek names were very fancy and difficult to spell, but yeah. Gwenel completed his PhD on FPGA CPU co-design for image processing in 2014. He has since been a research engineer at Time and Frequency Department of FEMTO-ST in Besançon, France, and it involved on developing the OscImpDigital framework for oscillator characterization. His presentation is about the CPU-FPGA co-design framework in the context of satellite communications.
Perfect, thank you. Okay, thank you, Mr. Chairman. So today we would like to discuss, so my colleague Gwenel Goavec and myself, Jean-Michel Fried, we're located at the Time and Frequency Department of FEMTO-ST Institute. That's an engineering institute in Besançon, in France. And we would like to discuss a framework that we've been working on for a few years now, which is focused on CPU-FPGA co-design. So we've had quite a few talks this morning about the Pluto SDR. So Pluto SDR. We had a few talks this morning about GPS. So what I would like to show you today is how can you try to take the best use of this to receive GPS. So the outline of the presentation will first to put us in the context of satellite communication. So in my case, satellite communication will be receiving GPS. And I'll try to show you why there is a very heavy computational load in processing GPS, decoding GPS signal. And in this context, then we will try to show you that we can offload some of the computational power into the FPGA of a Zinc CPU. So basically, what was presented this morning is that a Pluto SDR is an analog device's front-end AD9363 and a Zinc system on chip from Xilinx. Now, what analog device is doing is basically the Zinc is not doing anything. It's just collecting the data from the radio frequency front end and streaming this data through the processing system over USB, and the computer is doing everything. Two consequences. First of all, the FPGA could be used much more efficiently for pre-processing. In this case, we're going to show you that we can offload part of the GPS processing in the FPGA, so using a custom bit stream in the FPGA. And secondly, you are limited by the bandwidth on the USB 2. So you have 64 megasample per second coming out of the 189361. Obviously, in USB 2, you're not going to send 64 megasample per second. So if you pre-process to down-convert data at the FPGA level, then you can transfer to the processing system, so the CPU on board the Zinc. And if you do some preliminary processing on the Zinc, then you can stream a much lower bandwidth data set through the USB. So that's the outline of the presentation. Trying to show you how you can do this. And this oscillator imp digital framework tries to help you do this and ease the work of this co-design. So that's what Gwenel is going to show us. So let's get into the practical aspects of the discussion. If I can switch, okay. So why are we interested in SDR-based global navigation satellite service? I mean, there are a lot of hardware receivers. We've got someone here representing u-blox who's doing excellent GPS receivers. So why would you bother even doing an SDR-based GNSS receiver, global navigation satellite system receiver? So basically what I'm interested in as a physicist is to add more functionalities to a GNSS receiver beyond just locating myself on the surface of ground. So basically that's basic physics. If I want to do basic physics, reflectometry, if I want to use phase analysis of the time of flight, if I want to use reflectivity, I will not be able to do this with the output of a commercial receiver, because once you've processed the data, it's too late. What I want to do is to process the radio frequency information. Basically for me, GPS is a set of 30 atomic clocks rotating around the Earth. And these 30 atomic clocks, I can do a lot of things beyond just positioning, knowing where I'm located on the surface of the Earth. Second thing is I'm currently involved in a project about GPS spoofing, and you might know that now GPS spoofing is a €100 activity. Basically, with a Pluto SDR, as was asked this morning, you have GPS spoofing software on the internet, and it works very, very well. And so as part of my activity, I'm asked, how can you prevent GPS spoofing? And in my opinion, once you've spoofed a commercial receiver and you've got the processed output, it's too late. A properly designed spoofing system will be too late to detect. And my approach is to analyze the raw radio frequency signal coming to the receiver before it's processed as a GPS signal. So basically, what I'm interested in is having the observation of this constellation of satellite systems. 15742 gigahertz is exactly within the range of the Pluto SDR. And so all you need to do is put a bias T so that you can power the amplifier of the low noise amplifier of your receiver, feed the IQ stream 2 megabit per second, 2 megasample per second, that's one mega sample per second at the GPS signal, and run the processing. So, okay, the theory is quite simple. As we have been told this morning, GPS is CDMA. CDMA, code division multiple access, means that each satellite, all satellites are transmitting on the same frequency, and the way you differentiate one satellite from the other is that you have a pseudo-random code, gold codes, which encode each bit. So you have a stream. Actually, GPS is very slow. It's 50 bits per second. And these 50 bits per second are made of binary phase shift keying bits. And each one of these bits is actually the result of detecting the code associated, the unique code associated with each satellite. And so how do you find in a noisy signal, which is the sum of all the contribution of all the satellites, this particular satellite that you're looking for? You correlate. You correlate the signal that you're receiving with the known code. This is the important part. You have to know this code, and of course it's published by the US Air Force, so you know what the gold code is. And the property of being able to find one code and reject all the other is that these codes are orthogonal. So if you correlate the signal that you've received with the right code, you get 1. If you correlate the signal that you received with the wrong code, then you get 0. And that's how you CDMA will work. There's a little trick here in that this is all classical CDMA that's quite easy to implement. However, in GPS, well, GPS, our signals are sent by satellites, and satellites are orbiting the Earth, meaning they're moving. And if you do a bit of basic space geometry, you will find orbital geometry. Then you will find that actually these satellites flying at 20,000 kilometers over the surface of the Earth will induce at 1.5742 gigahertz a frequency shift of plus or minus 5 kilohertz. Now, considering the length of these codes and the length of the correlations, you cannot accept such a large Doppler shift. So you will need to try to find brute force search for all possible Doppler shifts until you've compensated for the Doppler shift that you received, so that the correlation will actually accumulate energy coherently in your integral. And what you can, if you do a bit of numerical simulation, you find that the Doppler shift that you have to search for is plus or minus 5 kilohertz with about 100 hertz steps. So what this means is that we're going to do a lot of correlations. Now, if you do a lot of correlations, you've got one way of saying this is a correlation is searching for the time-delayed copy, delay tau, of the code into the signal. So that's your correlation as a function of tau. And if you remember your convolution theorem, then doing a correlation, actually this looks very much like a convolution if you flip time, and flipping time is taking the complex conjugate of a complex number. If you remember your convolution theorem, then you take the Fourier transform of a correlation is actually the dot product of a Fourier transform. So searching for GPS is doing many FFT. And actually this FFT, what I'm going to show you is, because they're independent, they can very efficiently be implemented in the FPGA. That's the pitch of my story. While everyone will tell you that you should compute correlations in the Fourier domain, because this is thanks to the FFT, fast Fourier transform, you have an n log n algorithm instead of n squared. Well, actually in an FPGA, that's not so obvious, because FPGA are massively parallel. And if you implement the time domain version of correlation, you can continuously accumulate data as they are coming in. And so actually it's more efficient in FPGA to have the time domain version of a correlation. So we've been told this morning that for teaching signal processing, it's much more fun to do a bit of MATLAB experimenting. So I collected this data using my Pluto SDR. So I've got this file, a binary file with all the data that I've collected. And this was collected using GNU Radio. So you've got the script, read complex binary that allows you to read into MATLAB the data that you collected. And what I show you here is that in 10 lines of MATLAB, you can decode GPS. When I decode GPS, it's the acquisition phase. I'm not talking here about the tracking phase that was discussed this morning. So just acquisition, when you cold start a GPS receiver, it has to know what satellites are visible and what are their elevation and azimuth. It has to search. The only way you can do this is brute force. You can have assisted GPS, where Google will tell you what GPS is found, what satellite is found at a given place. But if you just cold start with no hypothesis, you have to brute force all possible satellites. There's 31 of them. It's not impossible. And you've got to search all possible Doppler shifts. Now, I told you it's plus or minus 5 kilohertz, except that your local oscillator is rarely an atomic clock. So your local oscillator will be offset with respect to the atomic clock of GPS. So you have to search a bit more than plus or minus 5 kilohertz. In this case, I did plus or minus 10 kilohertz. So just let me quickly go with you through these few MATLAB lines. Actually, about open source, this is all Octave. I write MATLAB because people are more familiar with the name. So you read your data. You say that your frequency range goes from minus 10 kilohertz to plus 10 kilohertz with 500 hertz steps. And you create time. So that's your classical software-defined radio approach. Your time is discrete, so you have to create time. Time is by steps of one over the sampling frequency being 1.023 mega sample per second. And then just 2 loops. You have to loop through all the possible satellites. We've got the script CA code, which you can find on MathWorks website, which is generating this pseudo-random code. It's a 1023-bit long code, so coarse average code, so it's the gold code of satellite number M. And once we've generated the unique code of each satellite, we loop through all the frequencies. We compensate for the Doppler shift, so mixing in the analog domain is a dot product in the digital domain, and you search for a correlation. Easy as this, and if you run this through all possible satellites, through all possible Doppler shifts, you find which satellites are visible in space, and by using their Doppler shift, you can know what is their elevation in space. So that's the basics of that's as easy as decoding GPS is. Now, for people who are familiar with MATLAB processing, you might realize that loops are forbidden in MATLAB. You all know that MATLAB is matrix laboratory. If you can express problems as a matrix, then it will go much, much faster. So here you see that we're looping through all the possible satellites. There's hardly anything we can do with this. We have to go from one satellite to another. There is no systematic sequence about the CA code. However, it's well known that the Fourier transform can be implemented as a matrix product. So these frequencies here are all independent from one from another. So just to show you how we can parallelize, and that's what we're going to do afterwards in FPGA, but just to show you how we can parallelize the whole story, in the beginning you do the same thing. You create frequency range, you create the time, you've got your data. But now, instead of creating sequentially all the frequencies, you create a matrix, and this matrix will be all the possible frequencies times the time. And this time you've got a horizontal vector, which is a frequency, multiplied by a vertical vector, which is time. And this product here will create a matrix. And the reason I reminded you about the convolution theorem is that the cross-correlation X-core function from MATLAB will only accept vector. It will not accept matrix. So when you want to do the correlation, you have to go back to basics. You're not allowed to write X-core of a matrix. MATLAB will not know what this means. But you're allowed to do a Fourier transform of a matrix, and it will do it in the column direction. So when you do the correlation, you go back to the basics, which is I compute the Fourier transform of a pattern. I compute the Fourier transform of the Doppler shifted signals, and the correlation is the inverse Fourier transform of a dot product of my pattern times the conjugate of my signal. So you see that you can write much more efficiently the same algorithm by parallelizing all these Doppler shifts and pre-computing the Fourier transform part. So here we got exactly the same result. Of course, it's formally the same thing. It's just that it's twice as fast. So if you do this in MATLAB, you multiply by 2 the speed of computation, or you have the duration. So basically, this analysis will take about 2 seconds on my will take about 2 seconds on my laptop using the loop system, and will take about 1 second when I parallelize this using the matrix product. Okay, so at the moment, we've got about 1 to 2 seconds per satellite, meaning that to loop through the 30 satellites, we need about 1 minute, and we are very far from real-time processing. Furthermore, the Pluto SDR Zinc here is only used for data collection, which is very poor usage of the available resources. So what we would like to do is the pre-processing on the Zinc FPGA, the correlations will allow us to unload some of the computation tasks on the processing system. So I'm using here the naming convention provided by Xilinx. The PL, the programmable logic, will take care of the fast data rate pre-processing, usually quite simple pre-processing, because programming the FPGA is always a burden. And then we shift the data at a high data rate to the processing system, the PS over the Zinc. And once we've done all the work on the PS, then we can stream the data through the USB. So that's basically the outline. Now, the big challenge here is, what are we talking about? We're talking about creating a new bit stream to flash the FPGA. We're talking about creating the kernel modules to configure these bit streams, these IPs in the bit stream. We're talking about creating the application for running all these tasks. So it requires many levels of abstraction in your software development. And this is where the oscillator imp framework, which we're promoting here, will help you to try to address all these layers of abstraction.
Thank you. This is the equivalent scheme for presented earlier, previously, but in the on the ecosystem context. Again, we have the array frontend. We have NCO. The NCO is used for the frequency sweep, and is mandatory since this component, the local oscillator for this component, take a long time to be reconfigured. So to increase the processing, we need to have something more quick to for the NCO for the frequency configuration for the transposition. We have a PRN. The PRN is generate all possible CA code available. We have just a switch to select which of them is used. The X core is a cross correlation in the time from with first input is output of the mixer. The second input is a PRN, and the all results are stored in a RAM. This RAM is available from the CPU part to, for example, to store in the file, to post-process. The user space application use the lib.io to configure at the first time the front end, exactly like done by GNU Radio. Configure the NCO. The NCO is configured with a driver, with a library. The library, because it's a bit complex, we switch between PRN to loop on all PRN, and we'll read directly in the through the driver data from the FPGA. This is the basic concept of the of our ecosystem. This is more generally the representation. We have an IP, the IP for FPGA, the driver is used to communicate with the IP with respect of the hierarchy of a Linux system. We have, depending on the complexity of the IP, we have a library to avoid duplication of code. We have an application. The application may directly communicate to the driver or through a library. And since an FPGA has no, with a FPGA, there are no way to discover dynamically which IP is present in the FPGA. It's mandatory to provide this information manually. The device tree is the official way for SOC system to inform the kernel Linux about which driver must be loaded and the base address of some information. The ecosystem is structured like this. we have a repository for IP, repository for driver, for library, currently only for tutorial, with a tutorial for the RedPitaya for starting with the RedPitaya, or for, of course, the Pluto SDR. This demonstration is available in this subdirectory. Globally, it's all about the structure of the ecosystem. There are some to have a coherent development. We have applied some rules. The first one is about the FPGA or the IP. First of them, like GNU Radio, we have two custom interfaces. The first one is a complex interface with an I data bus, a Q data bus. The second interface is a real type with only one data bus. This allows to connect two blocks to IP without glue between these two or complexity. And when two blocks are connected, it's okay. It's coherent data flow. We have control to specify when a new data is available, and on some specific case, we have an information to specify this data is the first of a burst, or this data is the last of this burst. For more for a development topic, we have splitted all block in more than one part. The first part is algorithm implementation. When we want to simulate an IP to verify the correct behavior, we don't want to care about, for example, the bus used for the configuration. So we have just to simulate this part to verify if the behavior is correct. Second gain about this is this part is specific to a protocol. If you change this by, for example, by default it's AXI, you use the Avalanche, you use the Wishbone, it's just mandatory to change this. The last thing about is the structure of the project. We have a project is split into the design part, dedicated for the FPGA, with a graphical design or a TCL design written by hand, and another part for the user space application with the device tree, makefile to cross-compile, the script to load everything, and finally, the most important part, the C file, the piece of code used to configure everything. Everything in red is automatically generated by a module generator, a tool provided by the OscImpDigital project based on an XML file. This file may be written by hand or automatically generated by analyzing the design. This file looks like this, with some optional option for example, for makefile, for cross-compilation. lib.io is mandatory for the Pluto SDR, for example, and the list of IP present in the FPGA, the type of the IP, the name of the IP. It may be possible to have more than one instance of the same IP on the FPGA, and most important thing is the base address used to communicate between the driver and the IP. And
so
no, it won't.
So as a conclusion of this introduction to OscImpDigital, you can see that in this case we've defined the processing chain. So of course you can treat the various blocks, but these are the various correlations, mixers, data to RAM, so shifting the data. So basically you can generate your own bit stream. This will be integrated nicely in the analog device bit stream. So basically analog device is sharing the repository for their own bit stream. Then we can just add our functionality. The original Pluto SDR functionality are not broken. This is added in parallel to the original stream. So this means you keep a functional Pluto SDR and you just add a correlation because you had plenty of space in your FPGA. So you just added a CA code decoding. So just to demonstrate here, because we've got the tiny 70,000, the tiny 7010 FPGA, we can only put one CA code decoder. With a single CA code decoder, we go from about 100 seconds on a laptop to 20 seconds on the Zinc, and current investigations are parallelizing the 31 PRN code on a bigger FPGA than the tiny 7010. So as a conclusion, we wanted to demonstrate, to introduce to you how OscImpDigital is a flexible framework for assembled signal processing, taking care of the consistency between the IP, the FPGA, the kernel module, the library, and the user space application. We have not discussed the fact that it's platform independent. We are using TCL script. These TCL script are calling whatever synthesis tool you're using, either for Altera Intel or for Xilinx Vivado. We have a consistent structure of a Linux application. We applied this to GPS decoding, and we're putting this to the bigger Zinc 7035 that allows us to run in parallel all CA code decoders. From my perspective as a physicist, I have no clue about what VHDL is doing. Gwen is working on all the IP blocks on VHDL, and even I can assemble them to use my own application. So feel free, as someone who's familiar with programming, with Linux programming, and who has no clue about FPGA, that this is a tool that you can use for generating your own bit streams. Resources are all available on the internet. We have build root for the Red Pitaya. We have build root, so the consistent toolchain, Linux, and library the generator for the Pluto SDR. This will nicely integrate into OscImpDigital that you can download, and you can check this on the GitHub. And just to conclude this talk, a shameless advertisement for our European GNU Radio Days that we're organizing. We organized a conference last year in Besançon. This year it's going to be in Poitiers, June 22nd, 23rd. Satellite and GNSS applications are in the framework of this presentation. So feel free to ask. We have some flyers, we have some advertisement, and please come and see me if there is any question about it. And thank you for your attention.
Thank you for the nice work. Questions?
No, not from EPFL. It's going to be dangerous.
Yeah, a question. It's a curiosity thing. So to look for the satellites, we've done more or less the same thing like you do. Of course, we also tried the trick about to the big matrix. But I was wondering, we never tried to make it faster because that's not our purpose. But I was wondering, shouldn't one be able to know roughly where the satellites are, just because you can store things or you can look up on the internet or so, and then have a rough idea. If you know that you are in Switzerland, you don't have to know that, and you know that the satellite is over there, you can probably figure out within a few, maybe 100 hertz what the Doppler is, and then you could limit the search to a much narrow windows. I don't know. Have you thought about that?
My understanding, I'm talking under guidance of guys who are doing the GPS, but my understanding is that that's the difference between warm start and cold start. A warm start, you already have an information about where you are located and what time it is. Cold start, you have no clue where you are. And when you have no clue where you are in a cold start, you have assisted GPS, where you ask Nokia or Google to give you a rough estimate of location from the Wi-Fi information plus the time, and then you have assisted GPS.
So they're doing that.
To the best of my knowledge, they're doing this.
Okay, thanks.
Other questions?
Is this only using the FPGA fabric? Is this processing only using FPGA fabric and not the processor on the Zinc?
I'm not sure I understand the question. Sorry. Here we're using both the FPGA, so we're generating a new bit stream with the FPGA taking care of correlation and generating the pseudo-random codes. Then we're using the processing system, the PS, the CPU, to fetch the data. And in this particular case, we're just using them to send, but GNU Radio is running on board the Zinc. So that's also one of the contributions of Gwen. Gwen has ported GNU Radio to build root, meaning that GNU Radio is not limited to just running on the laptop PC or the PC connected to the Pluto SDR, but actually here, GNU Radio is running on the processing system, which is the CPU, the ARM CPU on the Zinc. And then you can stream the data either using a 0MQ or a TCP/IP connection from the embedded Pluto SDR, from the embedded GNU Radio to the version of GNU Radio running on your PC.
Okay, I have quite a few questions too, but I will do one for now because we don't have the time. Assuming that I have a project and in Vivado and I want to integrate in a device like Pluto, let's say, which kind of modifications do I have to do in order to use your project? So what I have to do to modify on my Vivado project in order to use your
for a specific project.
Yeah.
Already, it depends, but basically you need to fetch the repository. You need to add the FPGA IP directory in your IP repository from Vivado, and you have access to every block available in this repository. And you add this. The rest is just to describe.
Okay, so right now you have a set of IP cores that are available on your repo.
It's possible to mix IP from, for example, for analog device, for Xilinx, or OscImpDigital IP,
so
or a custom IP.
Exactly. So if someone wants to use its own IP core, he can contribute back to you in order to integrate it?
Of course.
Okay.
Well, for us, the ideal solution would be that people adopt this framework and contribute their
Yeah, it's a nice idea. Yeah.
Of course, we didn't mention this is all GPLv3, so this is all open source and this is all accessible to everyone. So we're really looking for contribution. I mean, the interface has been documented. We did a lot of efforts for the last 2 years to try to document, to give tutorials so that beginners can get started easily. You don't even need hardware, actually. The first tutorial are just running by themselves on a Zinc with no hardware interface. So we're really looking for contributors about IPs, about adding new blocks, new processing blocks. This is what we really would like to integrate.
Or just a point of view of people develop this, and consequently it's interesting to have other point of view from other people to improve, to have better thing.
Okay, thank you.